So, first of all, a disclaimer. Yesterday I tried to make this talk and it took 45 minutes. So I will probably have to shorten some part in order to stay in the time limits. So the original title is Some Notes on the Integration by Parts Formula. And in order to get there, I have to give some introduction to notations and previous results. So the setting is, let's consider Banach space, the Banach space E of continuous functions from 0, 1 to Rn, and that is endowed with the Wiener measure, and in this way it's a classical Wiener space, and also the space of square integrable measurable function h. Notation are quite standard. And on this space, we define the Brownian motion, and by using the Brownian motion, we introduce the Wiener integral. Okay, so this is my way of setting, introducing the objects. There are several different ways, and Beppe the Prato is usually starts from W and then define Brownian motion and so on. But I think that this is quite similar introduction. Notice that there is not just one way to define the WH, because clearly it depends on the scalar product you're choosing in Rn, for instance. So there are actually infinite ways of defining the Wiener integral here. In any case, WH is a central Gaussian random variable with variance which is given by the L2 norm. And we define the first Wiener chaos as the set of random variables which are given in this form. Once you have the first Wiener chaos, you can construct the map of smooth random variables. For instance, by taking C infinity function with polynomial growth or other ways of smooth, other classes of smooth functions. And on this space, you define an object that we define that is a derivative, or we call it a derivative actually, which is a mapping from the space to LP in general E mu to the space of LP from E mu to H, defined by the formula that you see here. So you simply take the differential, the derivative and the direction xk, and then multiply by h. The idea here is that the derivative of wh is just h. This operator is closable, and this is a classical result. So once you have the closability of a diagram, so this is more or less the Maillard derivative that I know, and it is due to Professor Tubaro, which showed it to me. So you start from H, you define the first Wiener chaos, introduce S, you close it with respect to the norm, and then you define the Maillard derivative D as an operator from a domain that you call D1P to LP E mu to with values in H. Once you have the Maillard derivative, you can also consider its a joint operator that we call divergence, since the first one is a derivative somehow. And this definition is, again, quite standard, but let me just give you shortly what I mean. I just take a domain, and notice that in the general case, I have to take also the conjugate exponent q. And so since the derivative, the Maillard derivative was given in D1P, now we will consider a domain. This is dq delta. And dq delta is just, so delta v is just the operator that the random variable can be put in this formula in order that this formula works. And again, you have the possibility of closing this operator, etc. So this is closed and densely defined, and so we can use it later. And what is the format we need to use most is just given in this proposition. So delta applied to the product of f and u. F is a random variable, uses a random process. F delta u minus the scalar product of u and df. And so this is what is the commutator formula between delta and d. Okay, so this is the construction of my Levin calculus. I hope it was fast enough. Now, let me go to the setting of the problem. So on this space, we choose regular function g, and we want to construct the surface, a measure on the surface is defined by the level sets g equal r. So a few questions here. The first one is which kind of regularity is really required here? Into what is written below here. So this is my first example. So g of x is the L2 norm of x of t. And I also have a second example in mind, which is not written in the slides, but I can add it now. So take a functional u, which is which belongs, let's say, to L2 from E mu with values in E. And so you can define the analog of this object as GU, that is a random variable, and GU of x is just the norm of u of x at time t square in dt. So this is our second example. And the first example is given by the sup of the Brownian motion in the one-dimensional case. Cases 1 and 2 are in the n-dimensional case for n greater or equal than 3 due to some technical problem that we have and that we are not able to overcome, even if there are some hints in the literature that that should be possible to go to the case n equal to 1 and 2 also. And when I say we, I am very fast in my presentation, but when I say we, I'm talking about Luciano Tubaro from the University of Trento and Margherita Zanella, which is in Politecnico of Milano. And while for the part about example 3, there is also a joint paper with Tubaro and Giuseppe Da Prato. Okay, so what is the problem that we want to do? The problem we want to do is construct a measure that we call sigma, which is concentrated on the level set g equal r, that satisfies some conditions, some properties, and the idea is to follow the approach by Airo and Magliaven, which says, okay, let's start with this functional, the functional fx, which is defined on g less equal r, and try to prove that it is differentiable. And if it is differentiable, then the derivative should satisfy something like, well, formally derived here, you see that the derivative comes just in this point. And so the idea is that instead of having the less or equal, you should have something like the equality there. So this integral, which is written formally in the whole space omega, should be proven to be concentrated on g equal r. And so this is the aim, and there are a lot of papers that follow this approach in order to prove the existence of surface measures. So let's just see what happens. In our case, we want to extend to the case when you have a local kind of condition. And so we use this hypothesis that was first introduced in a different formulation, and especially in a completely different set, well, completely not, but in a related context and not in the same problem, by Noalart, that is given G, I want to prove that there exists a process U and a real valued random variable where the identity written, the identity 4 holds. And under this assumption, we are able to prove that we are able to prove the existence of this surface measure sigma r, such that the formula 3 holds. So the formula 3, I remember, is just the fact that f prime is formula 3 is just f prime x is just the integral on g equal r of x sigma. That was looking at the notation, so x of x sigma r dx, notation as above. And moreover, which is even most interesting for us, is the random variable g has a density that is continuous and bounded. And I have maybe enough time to give you an idea of the proof. So first we assume that x is a smooth random variable, so let's say at least in D1P, and we use a formula that is proved in the book by Noalart, that is that you can take the derivative of a function even if this function is not differentiable, but it's just Lipschitz. So this formula holds for our feed that is defined above. And then we can scalar multiply with u and then use the integration by parts formula and some other modifications. And so we get, starting from this formula, we get this other equality. And now we again use the fact that f is the expectation of the random variable that is on the left, on the right, sorry, on the right of this equality, and then you use the integration, so the duality between Magellan derivative and the square root integral to get the formula that is written here. And so you see that under assumption 1, if you take x equal to 1, so this part is not present, the assumption says that u over gamma belongs to the domain of delta, so this is integrable, and so this is a well-defined random variable, and so this object is well-defined. It can be used in order to prove the existence of the density for G. Then once you do this for x equal to 1, you return to the general case for general x, and you prove that also x times u over gamma belongs to some to the domain of the square root integral for some parameter theta, value theta that is depends on g and p that was given before. And finally, you say, okay, suppose that x belongs to D1P for p larger than n divided by n by 2. Okay, so this proposition is especially given for the first example. In the example 3, some similar conditions should be given. And in this way, you can prove the existence of the derivative fx of the functional capital Fx. And this is a continuous function and it is bounded by a constant times the D1P norm of x, so it's continuous and bounded as required. And in the last result in this part says that this random variable has a density which can be computed by starting from the density of G and the condition expectation of X given that G equal S, so on the level sets. Okay, so this is the main result that we want to prove in our paper. And so a couple of examples. So as I told you, the first example is suppose that you have an n-dimensional Brownian motion and define the random variable G as the H norm of B. The 1/2 is folkloristic in order to simplify the next formula. So you get that this random variable belongs to the space D1P for all P, and its derivative in the I direction is just given by the integral between S and 1 of BIT and DT, so it can be given explicitly. There is a very nice open problem here that I propose you. So open problem. It seems natural that not only this random variable is has a continuous amount of density with respect to the back measure, but that the same holds for other powers of BT. So what happens if you take G of Bx to be equal to the integral 0, 1 of the, so let's say B of X of T to the power, I don't know, 2K dt. So instead of taking just the L2 norm, you can take the LP norm. We know that for any T, the random variable BT is has finite moments for any order. So in particular, I can take 2n. I don't want to use n because n is the dimension of the space. So let's say 2K. Well, I have to prove it, and so if anybody knows how to prove that this random variable has a density, with these techniques or other techniques, it's not known, it's not written in the book by Borodin on Brownian motion. There are a lot of results, but not this one, nothing in this direction. Sorry. And well, this is an open problem. Sorry, have you submitted this as an open problem? Because we are collecting open problems, as you know. No, I didn't connect it because, well, it's not exactly a problem in the one parameter semigroups. So I was not sure if it can go there, but maybe I will do it. You're welcome. Okay, thank you. Okay, so let's go on. So I have the case of L2 norm, and we are in dimension larger or equal than 3. And what we want to do is, well, let's just check that this random variable satisfies the Maillard condition given in hypothesis 1. So I set gamma to be this integral, the integral of dsg in ds, which can be written explicitly because dsg can be written explicitly. And let's say u of s is given by dsg divided by its norm, so it's normalized. And it is possible to prove that this belongs to, so this satisfies the, if you remember, was something like u over gamma should belong to the q delta for some q. The problem here is that when you try to make the computation on the estimate of gamma to the power -1 over p, you get some problems which require the condition at larger than 2. This is a technical issue. We know for sure this because this random variable, so G, possesses a density for any dimension n greater or equal than 1, it is proved, can be proved directly, or at least with different techniques, but not using the Maillard condition. Okay, so this is another problem. once you have the density of G, you can use the previous construction to in order to define the surface measure sigma on the level sets G equal R, and you can prove the following result, that is a formula in the space, in the Wiener space, that says that exactly that if you take any x which is in D1P, and for any vector h such that x times the scalar product dgh is regular enough, let me just say this, then you have that the integration on the surface can be written in terms of the integration on the inside of the ball by this formula, where I recall that this is just an analytic notation, but on the right you have exactly an expectation with respect to the Wiener measure. And in particular, if you take x equal to 1, you get that the function the function f that we said before can, that is the expectation of WH when G is less than R, is just equal to minus the integral of dg in the direction h on the surface of the ball. And so this is a kind of divergence theorem for fixed h. So this is about the first example. I still have a few minutes, so I can go to the second one. The second example is related to the first, and it's given in the following way. Okay, no, so for the moment we studied what happens for the Brownian motion itself, and now I want to see what happens if I consider the solution of a stochastic differential equation. So let me just write the equation in this special form, so not a general solution, but let me just, we are in the case of a gradient system, and again, I need to recall that n should be equal, greater or equal than 3. We take a potential function, which is, let's say C3, so C infinity, doesn't matter, I will not go into details in this, and just define U to be the solution of this problem. In this way, we have, well, I recall the definition that GU of x is just the integral between 0, 1 of ux of s squared and ds. And I want to prove that also in this case, I have that the random variable GU is as a as a continuous amount of density with respect to the Lebesgue measure. And well, this is a very, for me, an interesting result. First of all, I can prove that this random variable has a density. So I will just use the notation for U for this is the density of G of U with respect to the Lebesgue measure lambda. Okay, so I can prove that I can compute this density by taking the integral on the surface, on the level surface of the Brownian motion with respect to the measure described by the Brownian motion with a density that can be given explicitly in terms of the potential function V. And the explicit formula can be written, can be seen here, and I will not read it, but you see it's how related to the Gaussian transform for our problem. And so this is interesting because I will use the same level sets as before and just use a density on this level set. However, we can also construct directly a surface measure on the level sets of GU, and prove that this density is given by the measure of the level sets of GU equal to R. And this is, so we have two different ways, if you want, to give the same result. And to go from one to the other is just a change of variable problem. Okay, so I still have 5 minutes. No? Okay, the chairman is not saying anything, so...
Yeah, sorry, the 5 minutes are for questions. But
the 5 minutes are for questions. Okay, so I just stop here and thank you for your attention.
Thank you. Thank you very much for your talk. So then, yeah, please feel free to ask questions. Okay, if there are no questions, you can use the 5 minutes to continue.
Okay, so thanks again. I have a question, but it's just technical. Do you want me to send the notes, the clear notes, or the one with my written?
Concerning the open questions or open problems?
I mean, no, I was thinking if you want the slides of the talk.
So perhaps